Like People, Time, USA Today, Reuters, MTV, these types of folks create content on a daily basis, hundreds, thousands, tens of thousands of pieces of content. And they need a way to track how users are engaging with them on a social level. Time series data, we've got a lot of it. Everything that happens in terms of tweets, Facebook likes, LinkedIn shares, anything across the major social networks, these are all things that content creators want to know about. But what's the important stuff? Right? Like, that's something that people really haven't figured out. And that's something that we're working on figuring out. Because there's all these disparate data sources. You know, you get a little bit from Facebook, you get a little bit from Twitter, you get a little bit from LinkedIn, a little bit from Pinterest, but what does it all mean? Right? And if everybody who was creating content also had to try and figure out what the best thing to do along social media was, you know, that creates a situation where everyone has to know everything about everything, and that's not what anybody's after. So what we've done here is we've created a dashboard that allows content creators to take a look at what they've published, and it's sorted by, you know, what we believe, based on all the social actions, is the most social piece of content for them at that time of day. And it allows them to do certain things like decide spend, and even help decide what content to publish further. We look at millions of URLs every day. So clearly, right off the bat, that's a big data problem. Because not only are you finding out what's going on each individual URL, but you're also finding out all the social actions that take place around each individual URL. That translates to over 1 billion page views per month. The B word's a fun word because that means that everything that you've done that's previously worked will probably no longer work. So it's a total change in scope, which again is why things are an evolution. Because everything that worked with a few 100,000 URLs is not going to work with a few million URLs. Unless you did it right the first time, in which case I'd like to hire you, because that doesn't happen very often. We look at about 250 million events every day. It's a small number right now, but it's growing. And that's talking about across every social network that we track. We use the Amazon cloud. And we do that because everything we do needs to scale up and down with traffic patterns. At any given time, we're using between 90 and 130 machines during peak and lulls of the day. And with all that information, we built a predictive measurement algorithm to measure the social web. So where did that start? Well, we started out with Rails and Mongo, because we figured we've got a few assumptions, let's test it. And we did. And then we started becoming successful, and we realized that that would not work. Because when you hit scale, most of your early assumptions stop working. So what does it look like now? We've got a significantly more complex system. In order to meet the demands that our customers have on us and being able to use and visualize and understand our data at both a granular and a macro level, we had to put a few things together. This is not exactly what one would call a homogeneous environment, but what we have works for us to get things done. And this didn't happen overnight either. This is 2 years in the making. So how did we get there? Well, we knew that we needed something that could handle a lot of volume very, very quickly. Because once you start taking in a few thousand events per second, after going from a few events per second, you need to make sure that everything that comes in gets stored. You can always process it later, but if you didn't catch it the first time, you're probably not going to get a second chance. Really fast writes to many locations. This is another way of addressing it has to be there in order for you to recognize it. Query by column groups. Well, this is a really interesting problem that works well for us. If we want to pull all the tweets that happened on a particular article in a particular time frame, we can do that because we can say, just give me all the tweets. If you tried that in MySQL on a table that had 5 million rows, good luck. Because we did, and it didn't work too well. We like TTLs because we don't need to keep all the data forever. We can just say, this data is good for 30 days, and then at the end of 30 days, a terabyte of data just disappears. And if you're not sticking around cleaning up a terabyte of data at the end of every 30 days, your life gets a lot easier, especially when you have to do it across multiple systems. The other problem that we ran into is we were a very heavy Node.js shop. And when we first started with Cassandra back about a year and a half ago, the Node.js driver had a whole bunch of memory leaks, and we found that if you ran it for more than 30 to 35 minutes, it would crash, which is not fun when you're trying to keep a system with 100% or so uptime. So we ended up having to roll our own driver. And this is one of the things that you may have to deal with early adoption, but thankfully, he's not in the room at the moment, but the guy who was up here before, he wrote the driver for Node.js for Cassandra, and we have not had that problem since. We've had other problems, but that driver crashing was not one of them. And the other thing that we really like about Cassandra is that the distribution amongst availability zones and regions. It's very useful. It keeps our uptime. We've actually been the Amazon outage that happened a couple months back, where an entire data center went down, one of the availability zones. We didn't even notice. We got a few alerts, but none of our systems complained other than, hey, I can't talk to the Cassandra servers, and we ran just fine. So why do we use Mongo if we went to Cassandra? Especially because a lot of people put them in the exact same category. Well, one of the things we really like about Mongo is the atomic increments. It's incredibly fast. Because a lot of the stuff we do is with JavaScript and in Node.js, it drops down to the wire, sends it across in the BSON protocol, and as a result, it is fire and forget. Those increments happen faster than on most Memcache or Redis servers. And I'll get to why that happens in a minute. Yesterday, Mongo released their latest version, which includes hashed shard keys. This was a real problem up until yesterday. We haven't actually upgraded, but this is a huge win for us. We were doing application level sharding in Mongo, and although it was handy, it definitely created problems. It is a benefit because you can still distribute your keys, but you still end up with hotspots. One of the other benefits that Mongo gives us is that it's a great ORM. It has a Mongo ID or Mongo mapper, depending on which one you want to use. They work very well for Rails, and Rails is our front end. There is no such thing, as far as we're aware, that works as seamlessly with Rails as Mongo ID, but this happens to be one of them. Mongo also gives us B-tree indexes. Until Cassandra provides some support for deterministic indexing, we can't do range queries. You can do range queries where you reduce the cardinality, like with secondary indexes, but on really, really large data sets, your return times, your query response times are just not going to be sufficient, or at least they weren't for us. So being able to have access to B-tree indexes of aggregated data, which is what we store in Mongo, is very handy. We also get to take advantage of document-based stuff. We store mostly aggregated statistic collections in Mongo, and that's why documents work very well for us. And again, TTLs. When you can just get rid of, we don't exactly have terabytes in Mongo, but when you can get rid of tens of gigs, or in some cases hundreds of gigs of data at the end of 30, 60, 90 days, it also becomes very handy. Redis. Why do we use Redis? Well, it supports hundreds of thousands of transactions a second on a single box, which is great because you don't have to have n number of nodes. But you do have to have n number of nodes for your fault tolerance. You just don't have to have it for the basic running of the system. It's a great caching engine. It supports great useful variable types. We use a lot of these variable types before Cassandra supported them in 1.2, so we needed this to be readily available. The other thing is that everything's guaranteed to be memory mapped. Because Redis is pretty much all in memory, everything you do is going to be fast when you query it. It's got great support for transactional operations. You can roll back if you really need, because you can do that on the application side. And it's a centralized queuing and locking system. I know John talked this morning about the attempt to bring that locking system into Cassandra, and they're still working on that, but in the interim, we use Redis as our queuing and locking system. And what do we use InfoBright for? Well, if you don't know what InfoBright is, it's a MySQL-based column store, which is basically storing the columns vertically rather than horizontally. When you think of the normal way that MySQL stores data, the way you envision it and the way it comes up to you in the console horizontally is exactly the way MySQL stores it on disk in most cases. Column store is stored the opposite. If you were to just slice out that vertical section, that's the way it stores it on disk. So you can do things like aggregating along the column much, much more quickly. So it allows for ad hoc queries. It works with the standard MySQL driver. It's great for ad hoc analytics. You get great compression of your data, and it allows for pre-aggregation. So if you have a whole bunch of numbers, say that the ages of people in a column, you can find the mean because it will store that in advance. It'll store that on the right. So it's just like one of the other pre-aggregated databases, but you can run ad hoc SQL style queries against it. So why do we have so many programming languages? Well, we got a few reasons for that. The biggest is each language has its own benefit, right? For us, in order to really understand the social space, we found that although we started with Ruby, and Ruby's great for quick development, and especially for a lot of the web work, it just didn't support all the data science stuff we needed. And if there was a little graphic for R, rather than the letter R, I probably would have put that up there too, but frankly, the letter R is just not as cool as a gopher. So we use Python for a lot of our data science, and that's what our data science team spends most of their time with. We do a little work in C as well, but for the most part, we stick with Python. So everything that we do that needs to access any of our data stores, we need to be able to access in Python. Anything that happens on the front end, it needs to be able to work with Rails. Rails is usually in most cases, the intermediary layer between what the users on the front end see and what the back end has access to. And the only thing that sits in front of Rails is Ember. Ember.js, more specifically, is a JavaScript framework that allows real-time updating of your views. No real need to go into that, but it does allow us to transform pages on the fly, which is something that we really like. Each language also has its own development benefits. So Python is very easy for data scientists to learn. So when they come out of the math world, not really knowing much in the way of engineering outside of MATLAB, it's pretty easy to teach them Python and get them going. The other thing we really like about all of these languages, and the one thing that's consistent across all these languages, is they speak JSON. And the reason that it's important is because we have a whole bunch of data stores, we have a whole bunch of languages, and we need a uniform communication layer. We were going to choose XML, but we don't hate ourselves, so we decided to stick with JSON and build all of our APIs to speak JSON. But what does that all mean? Sometimes, even though you have a single great idea, it may not come out exactly the way you want it to. So there's a problem to doing all this. Each data store and each language does come with its own cost. So Redis, it can only use a single core. And if you want to get one of these beefy 8-core machines with 64 gigs of memory in Amazon and just start throwing everything at it, that's great, except it will still only use one core. So the way we solved that was we took one of those great 8-core machines and we stuck 7 instances of Redis on it. Did CPU pinning and made sure that anything that we wrote and any transaction, we knew that we were going to have to pay the serialization, deserialization price for anything string related. And that may not seem like a lot, but when you're doing tens of thousands or attempting to do hundreds of thousands of transactions a second, that serialization price is a big deal. InfoBright, we found out the hard way that you cannot delete or update anything. We did try once. We tried to delete one row, and when it wasn't done 3.5 days later, we decided that it would be easier to unload the whole database and reload it without that row. And believe it or not, it was much, much faster, because that took 45 minutes. So again, you need to know the trade-offs that you're making. And the big trade-off that we had with Cassandra is that it didn't have B-tree indexes. And I explained a little bit why that was important, but if you want to be able to run range queries, that's going to be a problem. And that's going to be a problem as your data set size gets larger. If anybody's used Mongo at all regularly, there's 2 things that you'll probably notice. First off, that the indexes have to fit in memory, and if they don't, you probably won't be able to even log into Mongo, because it's just gonna wave, it's gonna smile, and it's not gonna really do anything else. The other thing is that if you run it in the cloud, you'll find that they have a replica ping time that's forced on you. Mongo has this idea of the least amount of tunables possible for a working system, which is great in theory, unless you want a working system in something that's not ideal, say the cloud, something that you can't predict what the latency is going to be between two machines at any given time. So you'll find that machines will drop in and out of your replica sets pretty much without warning, and that's not fun at 3 in the morning on a Saturday. Python, it's great. Unless you like formatting your code your own way. It's really a minor complaint, but when you're trying to standardize across how many engineers and data scientists and teach them along the way, it does present a few code problems for teaching. Also, the community, and I'm not trying to start a flame war, community is not great. We'll just leave it at that. But we do use it a lot, so I'm not complaining about Python itself, just the community. Ruby, we tried it, just wasn't high performance enough for everything we wanted to do. Right, we tried the crypto libraries, we tried the stats libraries, and we found that everything we tried just took much, much longer in Ruby than it was in Python. And we were a very, very heavy Node.js shop, and we still use JavaScript very heavily as well. But we found that the exception handling is rather limited, and having to bubble everything all the way up to the top if you get an unknown or an unexpected exception is not only very costly to the application, but most programmers eventually start to hate it, even those who love JavaScript. So what's the takeaway? Well, the takeaway is very simply that all this stuff takes a lot of work. All these lessons that we learned and all these things that I'm presenting in a single line, they took us a long time to understand and to really figure out where the problems were. So one of the biggest lessons we learned was building everything to conform to a single standard. And to do that, we built a service-oriented architecture, and what we like to refer to as our internal API. And what that is it's basically a layer that you can ask any question to, and it knows where to get the data from at any given point. So we have all these data stores and all these languages. So you just use that JSON layer, communicate over HTTP, ask the JSON, ask the API for whatever you want. Say if you want to find out the last 12 hours, what happened over the last 12 hours in a particular piece of content, it'll go to Mongo for the most recent hour, it'll go to Cassandra for everything that happened within this UTC time period, and then prior to that, it'll go to InfoBright for the rest of the data, and it'll return all of it to you in a single JSON response. And that alleviates the developers from having to know anything else other than I need to ask one particular location this question. The other thing you have to worry about is your data accuracy. When you're dealing with multiple data stores, you need to know that what data looks like in one place is what it looks like in the other place. And the only way that you can find out that it's wrong the first time is when someone else, most likely external to your organization, says, A doesn't match B. So how did we handle that? We started out writing checks programmatically, and we found out that sometimes that works, sometimes it doesn't. So we had to spot check. Once we figured out what we were spot checking regularly, we were able to write slightly more programmatic and ultimately algorithmic tests to see, does this data make sense? And the biggest reason for this was when you're dealing with things that are external to your organization, like data that you cannot control. For instance, in our case, we deal with all the social APIs, Twitter, Pinterest, Facebook, LinkedIn. These guys deal with massive amounts of data as well. And sometimes the eventual consistency bug bites them too. They'll send down data that just doesn't make sense. You'll look at an article that has 500 tweets, and then you'll say, hey, Twitter, how many tweets does this article have? And they'll be like 7. And you're like, well, that's not really possible. And you can ask them again, and they'll be like, no, we're sure it's 7. And then you're like, I don't know about that. You just told me it was 500. And then you ask them again, and they're like, no, it's 504. And that's really confusing, especially when you're looking at it against multiple data stores. So in order to understand how to make those differentiations, you need to first figure out where the problems are. And that's a lot easier to do visually most times than it is programmatically. So the other thing that this service-oriented architecture allowed us to do was it allowed us to build a framework for testing. And what's really cool about this is that anytime we want to test something new, we don't actually have to bring our system down. If we want to test a new queuing system, say right now we use Redis, but we're putting NSQ in there. And we tried RabbitMQ for a little while. We didn't have to bring anything down. We just had to tell our queuing system the things that enqueue the jobs to not just enqueue to one place, to enqueue to 2 places, or enqueue to 3 places. So we can test Rabbit, we can test NSQ, we can test Kafka, we can test whatever we want. And the same thing goes with storage engines. When we want to test a new analytics store that's SQL-based, all we do is just say, instead of querying it in one place, query it in 2 places. And there's no downtime incurred by just adding another system. It's just like any other rolling deployment. And the other major benefit is that you get access to all the toolkits that have been built for every single one of these storage engines or queuing engines or programming languages or whatever you get to take advantage of. And one of the examples I like to give is Mongo has built this, Tengen, the folks who make Mongo, Tengen, have built this great system called MMS. And it works very well, it's just not great to look at, right? It just tells you how your systems are doing on a superficial scale, right? It shows you some graphs, tells you, your flush times, things that are important to the system level side. And then DataStax built this thing called OpsCenter, right? And if you use DataStax Enterprise, OpsCenter is basically this interface that tells you on a low level or a high level exactly what your systems look like. And it's much, much nicer to look at. And the benefit is that we get to look at how the systems are performing in a nice way, and if we really want to, feel bad about ourselves, we can go look at MMS and be like, all right, we got to look at both these tools, but we can go back and leave on a good note by looking at the prettier one. Might not seem like a big deal, but try looking at crappy stuff all the time and see how you feel. It really helps the mood. So what does the service architecture really look like? Sitting behind that internal API is just how the systems look. The internal API is the guard, right? Nothing goes past, nothing queries those things directly. The internal API holds the drivers for all of those systems, and as long as the developers don't need direct access, and there really isn't a need for them to have direct access, they can go straight to the internal API and ask any question and have it returned to them concurrently. The other lesson we learned is trying to keep the path of the packet consistent down the line. And what does that mean? Well, for example, if you have what comes in from the internet on one side and the data stores on the other, just traveling down, the first set of diagrams that you see that are yellow, we take a look at the Twitter fire hose. We have our event processing systems, which handle things like page views and refer accounts. The APIs, which are the Facebook and Twitter API for things that they don't pass down the fire hose. And then we have collection systems for like Google Plus and other tiers that don't give us direct access that we have partners for. Everything that comes down the line gets immediately dropped onto the queuing system. Once it hits the queuing system, it's picked up by a consumer or a worker. The worker then accesses the API to ask any questions that it needs to process the data. The internal API will then ask the questions of the data stores and then pass it back to the consumers. This way, if there's a breakdown, you know roughly where the breakdown happened, because if the packet made it this far, it had to follow a certain path. This is not an immediately obvious fact, because ideally you want the quickest path to your information. But if you don't keep this highway, so to speak, it's very easy to lose track of how your data gets from point A to point B. The other thing that we did is, this is how we distributed our architecture. When we put everything into the cloud, like most people, we were like, US East 1A, just spin up more machines in US East 1A. And that was great until US East 1A went down, and then so did we. Everything went down. So what we did was we took a look at the distribution of our data and the distribution of our systems and said, okay, if we have one node of Cassandra in US East 1A, one node in US East 1B, and one node in US East 1E, and you can go with any one of the data availability zones you'd like, but if you have one in each one, as long as you have different pieces of the replica, if you have an RF of 3, then you can tolerate losing an entire data center and you won't even notice. And that's actually what happened to us. And the same thing goes for all of the other system types. But the key here, and the key here for us, was having this internal API be accessible across any one of these, across any one of the availability zones. Because when you ask any one of the internal API servers, it knows about the systems in the other availability zones, but it's going to be more partial to its existing availability zone, where it sits for the faster response times. So, like I said, it didn't really bug us. We lost an entire availability zone, and it didn't bug us. If you were in the last talk here, you heard Matt File say that 90% of the people that use Cassandra on the cloud are in Amazon. And there's a reason for that. At least in our case, you see every couple of weeks Amazon, if you're on their marketing mailing list, they'll send you out a few new features. And every time they send out a new feature, you always wonder, like, can I use this? Can I not use it? Can I take advantage of it? Is it useful? Is it useful for me to learn this stuff? Well, in some cases it is, in some cases it isn't. For instance, we tried to offload our queuing system onto Amazon because we figured, hey, these guys probably got it right. Like, they work with a lot of large-scale systems. So we tried to offload our queuing, remove it from Redis, and we figured out that for us to maintain our own queuing system would cost us roughly $2,500 a month at the time. This was just given our workload and the machine cost. So then we tried offloading it onto Amazon, and we found out that after a week, that extrapolating the cost out would roughly equate to about 15 grand a month. It made our lives a lot easier, but not 10 grand or 13 grand a month easier. On the other hand, when we wanted to offload some of our scaling, when we needed to do just simple web services scaling, Beanstalk allowed us to spin up a new Rails app with the Ember front end on it, with all of our cache data sitting on that machine, and it cost us less than half of what bringing up a new instance would cost just to handle that traffic period. So the reason that people run in the cloud isn't just because it's cheaper or more highly available. It's because the services, or at least for us, it's because the services that they offer and that they are continuing to offer make both the job of the developers and the people that do the ops in our systems, that makes their lives a lot easier. And just even going down the list, you can see that that most of these features weren't around 6 to 9 months ago, and I think other than maybe the queuing service and Redshift, we probably use all of them at SimpleReach in at least one form or another. But to really take advantage of all of that, we really needed to figure out a good way of expanding the role of what one person was capable of doing. So we have one really, really smart DevOps guy who is insanely overworked and probably not too happy at that fact. But once Amazon came out with OpsWorks, which is essentially an extension of Chef, we already use Chef a lot in-house. And for those of you who don't know, Chef is a configuration management system. We started out with me logging into every machine and installing everything that was necessary by hand, copying binaries, bringing the data over, and ultimately hating every single person that I came in contact with after setting up a machine. Once we realized that wasn't scalable for me or anybody in my immediate vicinity, we decided that we would shift over to Chef. Chef allowed us to bring up a machine just by saying, I want another one that looks like this. And then Amazon came in and said, you know what, we can do better than that. You can just build these things yourself. You can build a template yourself. And rather than saying, I want another machine that looks like this, you can say, I want another machine that looks like this in this availability zone, another one in this availability zone, and another one in this region, and have them all talk to each other via these security groups. And it does all the security groups, the firewalling, and everything else for you. And oh, by the way, you can add it to your monitoring stack because we handle part of that too. And not only did that take the onus off of me, but that made things really easy for the folks who actually have to manage the systems. It also made our deployments easier because, again, any time that we needed to deploy something, it didn't just become a matter of spinning up the machine, building Nginx, building Rails, deploying the latest code base. We would just say, give me one that looks like this, and deploy this code hash from GitHub. The other thing we did is made really extensive documentation because if our DevOps guy gets hit by a bus, and I know everyone loves that scenario, if our DevOps guy gets hit by a bus, not only will we all be upset, but that means hiring somebody to do this will be significantly easier than me going back to wanting to hurt people every time I had to set up a machine. So let's pretend that nobody listened to anything I said for the past however long I was talking. The biggest thing I want everybody to take away from this is that after 18 to 24 months of doing this, it just takes time, right? Like every lesson that you need to learn, every time you're going to add to a system or every time you're going to increase your architecture, it's not always easy to get it right on the first try. Sometimes you gotta fail. Sometimes you gotta do it wrong, and that's okay. I mean, you can make a couple of mistakes as long as you've learned from it and you don't make the same mistake twice. You also should know when to build your own tools, when to use existing tools, and how to integrate the tools that are out there. And again, there's a lot of folks that stick strongly to use only. There's a lot of folks that stick strongly to build. But I feel like in the best environments, you evolve the best tools that not only work for your organization, but that work for the people in your organization. Another lesson that we learned was just abstraction. If you don't need everybody to know how to use everything, don't force everybody to learn how to use everything. It's great that the developers will want to learn how to use Mongo and Cassandra and Redis, and there should be an understanding at that level. But ultimately, if everybody needs to know everything, then nobody's going to be an expert at anything. Distribution. This is an architecture one. Do your best to not pigeonhole yourself into US East 1A, because as you will undoubtedly find out the hard way, when US East 1A goes down, so will your spirits. And the last thing is monitor everything. Automation does not come easy. It takes a lot of time to build up to the point where you can automate things, but it will ultimately make your life easier. So once you figure out the best processes for you, and once you figure out the way that your system works and the best way to keep your systems working, automate ways to get yourself there. And I just want to leave you with something I alluded to at the beginning. Revolution only lasts 15 years, a period which coincides with the effectiveness of a generation. And in theory, this is great, but let's even take that down a notch. Ideally, you're not going to be with your company for 15 years. I mean, it's just not going to, it would be great, but it's not going to happen. So when you set things up as if you were you were going to be the next person walking into it, right? Evolve the systems so that when it's time for you to move on, that somebody can walk in and say, I understand what this person was thinking, not, I would love to kill the last person who had this thought. The new thank you slide, the new thanks for listening. So if you're at all interested in anything I said, we are hiring, and we'd love to talk to you. So I've got some time for questions. If you got any, I will do my best to attempt to answer them. Go ahead, I can repeat the question.
Can you get into some more detail on how you manage the data flow between these disparate storage engines, like going from Cassandra to MongoDB to Redis?
Sure. He asked how we manage the data flow from going to the various storage engines. So if you remember back to the slide about the path of a packet, ideally when you have that worker system, right, that worker, when that worker asks the API for information from the data stores, the worker says, I know where this data ultimately needs to end up. If it's a piece of data that needs to be available immediately as a real-time number, then it's going to go to Mongo, because our system uses Mongo for almost everything that we do in real time. If it's going to need to be cached at some layer or invalidate a cache, it's going to go to Redis or make a query to Redis. And anything that needs to be sort of ETL'd, and in the sense where it's going into a more permanent store, something like MySQL, where you can't do the adjustments, you can't do the updates, you can't do the deletes. Then we put it off to the side in a separate queuing section where we say, come back later, process this differently, and if there's anything that we've learned about this that may invalidate it, let us know then. For instance, To go back to my example with Twitter, if Twitter says, you know, hey, this thing's got 500 tweets, now it's got 7, and then it's got 504, and we, you know, during that period of time of, say, we use the granularity of a day, if that's changed, and then we go to do our daily roll-ups, and we're like, whoa, this makes no sense. Like, you will never see tweets drop by that much. Then we process it and say, okay, we're gonna get rid of this middle data point. Most likely, it's only gone up 4, and use that final loop. So it's essentially ETL processes and the worker processes that decide what goes where when, and all of that is based on what the requirements are for the system. In some cases, our clients say, we need real-time data on X, Y, Z, and we need it, and real-time has its own definitions, but in some cases they need it within a minute, in some cases they need it within 30 seconds. It's not like the social data in this case is not like the financial world, it's not microseconds, it's, you know, sometimes a minute. I mean, we can get away with, you know, a minute, minute and a half in some cases, but for the most part, the workers decide what goes where, when, and that's decided in advance.
If you could do it over again, what would you do? Would you eliminate certain parts, certain technologies from your process, stay so standard, or do you use all of those technical components that works right?
So he asked if I could do it again, would we get rid of anything, would we change anything? And the answer is no, we wouldn't, because the problems that we have to solve, there is no one size fits all. There is no single solution that does everything that we need. In some cases, we need to organize the data in a purely chronological way, and that's pretty easy because, you know, with Cassandra, you just store it by date. Well, if you want to store it by date and by count, you know, you can't do that because you can't order your counters like that. You know, there's no, Cassandra doesn't let you do that. So we need to store our counters in Mongo. Then we can slice out then we can, you know, run a range query and find out what we need. You know, you can use Cassandra to a certain extent as a caching engine. You can use Mongo as a caching engine. But ultimately, the fastest caching engine there is probably going to be Redis, because the nature of what it does and the nature that you can guarantee that everything is memory mapped just serves better for caching most things than, say, Cassandra or Mongo. Each piece has its own value. And when it comes to things like the analytics and running ad hoc queries, most people are just more familiar with SQL. And even though things like, you know, even though CQL is attempting to build that, there is no comfort level that BI folks have with, you know, CQL, and probably won't for a while if they do. So if you put a business person who's comfortable with SQL in front of a CQL terminal, they're probably going to look at you crooked, right? So, you know, that piece of the architecture is also very important and is also a requirement that's given to us. I'd say that the only thing that we probably would have done sooner is built the intermediary layer, that service architecture earlier, because early on we were doing everything direct to the data store, which meant that every engineer had to know how to not only effectively write to every data store, but needed to know the schema and the storage pattern, and all that stuff took probably longer to figure out and or document than we would have liked to, and it probably killed us on the development time. Yeah, it's a hybrid. Sure.
I think you mentioned using Amazon as a cloud hosted provider. How do you think if I want to swap out because of cheaper solution or better solution? Just for a second, there are competitors like Rackspace, even Google, I guess, but mainly Rackspace is open cloud and they're making some noise. How do you swap in and swap out, say, to another open cloud solution?
Well, that's why we went to something like Chef, right? Because Chef just says, here's what the machine should look like. Chef says, if this is, I mean, we're very particular with using Amazon Linux, but if you wanted to use like CentOS or something as your base image, you can say, I'm going to use CentOS 5.6, and CentOS 5.6 is going to look pretty much the same on Rackspace or Amazon. So you say, I want CentOS 5.6 with all these packages, spin me up one on Amazon, spin me up one on Rackspace, and then do whatever you need. Well, the queuing itself is just merely an application that sits on top of one of those systems. If we're using an Amazon-specific service, then yeah, then we have locked ourselves in a little bit. But and we don't do that in all cases. There are, yes, that can become a problem, but it has not yet to date.
Real quick, we'll take one more question. And just again, reminder, on the 8th floor, you can head up there to meet the experts and speakers, and all the experts will be up there for questions and conversations for the entire afternoon.
I noticed I noticed you're using Redshift Analytics. Curious what gap that.
We actually didn't end up using Redshift. We were part of their alpha program because